Hello. Today we are going to discuss our new lecture on size dependency in nanostructure of nanocoatings. So the main aim of this particular lecture or maybe some next subsequent lectures are that how the nanoparticle size is actually creating some advantages for the coating purposes. The thing is that when we are talking about the nano composites or nanotechnology or maybe that small nanoparticles, always we are talking the term nano. So nano is nothing but the 10 to the power minus 9 meter. So maybe earlier days or maybe the past times when people were using this kind of particles, maybe that one is into the micro size. But in this particular lecture or maybe next subsequent lecture, we are going to show that when the same materials we are using into the nanometer range, the properties of these particular composites or maybe the coatings is totally changed. So first, before going to see that what is going on inside the matrix, just let us take a note that what is the role of size in nanotechnology. So the basic construction of nanomaterials has formed by nanometric scale engineering. So as I told already, whatever the particles we are going to use, the size of that particles is 10 to the power minus 9 meter. So generally the particles on an average diameter of 1 nanometer to 100 nanometer, we are calling it as a nanomaterials or maybe the nanoparticles. So that size particles actually we are going to use for this particular purposes or maybe for these particular applications. So on such scale, specific or completely different material indicates the possibility to create more accurate new materials and devices with the vast capacities. In our last or maybe past few slides or maybe lectures also we have seen that when we are changing the particle size from macro to micro or maybe from micro to nano, the same properties is changing hell and heaven. So here also we are going to give some examples, like the scale of nanomaterials should be classified from 1 to 100 nanometer, what I have already discussed, which means cluster or atomic nuclear palette with no less than 100 nanometer, fiber less than 100 nanometer in diameter and film thickness less than 100 nanometer. So whatever the particles I am going to use or maybe whatever the fibers or maybe whatever the pellets I am going to use, the size or maybe the diameter of that particular nanoparticles is less than 100 nanometer. So as an interesting example of the size dependency, plasma electrolysis has been used for fabrication hard nanocrystalline layers on commercially pure titanium. These samples have reported different average size of nanocrystallites. So when we are talking about the properties, generally that properties is depends upon the two things. First one is known as the particle size of that particular nanoparticles and what is the coating thickness. So first one is known as the crystallite size of these nanoparticles and the second one is known as the coating thickness of that particular material onto the substrate itself. So based on these two diameter or maybe the size, only that nanocomposite property nanocomposite is showing different kind of properties. So here this is also an examples. So these samples have reported different average size of nanocrystallite. So from this particular figure we can show that ACM image of nanostructures with average size is having 32.6 nanometer crystallite size, and here the crystallite size is little bit bigger, which is 95.1 nanometer. So in this particular case we can see that these materials crystallite size or maybe the nanoparticle size and these materials the crystallite size or maybe the nanoparticle size is totally different, and in future I am quite sure that they are going to give the different properties in terms of their crystallite size. So in this range, generally 1 to 100 nanometer, when we are using this kind of materials, nanomaterials show specific properties whether which they did not show for bigger dimensions such as micrometers and higher levels. So as I told already, the same material, the same substance, if we are using in a bigger particle size or maybe the crystallite size of that particular particle is bigger, then it will show something different properties, but if we reduce the size of that particular crystallite, it will show some better properties. So this effect which has emerged due to the size of nanomaterials is known as the size effect. So, when we are dealing with the different size of that particular nanomaterials, the technology is known as the size effect of that particular case. So, here are the some examples. So, it is a broad examples because there are n number of examples or n number of materials we are trying to prepare by which we are getting different properties. Here we have try to give certain kind of nanoparticles or maybe the nanofillers or maybe the nanomaterials which we are using in our day to day life, which you are using for the industrial purpose or maybe some kind of electronic purpose, optical purpose, biomedical application purpose or maybe any other purpose. So, here it is a like a list of examples that where or maybe how or maybe what type of nanomaterials or maybe the nanoparticles we are going to use. So, here we are using that materials in the nanoparticles on maybe the nanocomposites, then nanocapsules, nanoporous materials, nanofibers and nanowires, quantum dots, carbon based materials like carbon nanotubes, graphene, fullerene, etc., and the thin film. The same thing into the pictorial view we have given over here. So, here we are giving the picture of some kind of porous materials, then we are giving the picture of some kind of fibers, then some kind of wires, then we are giving the thin films, then we are giving the picture of carbon nanotubes, then we are giving some kind of carbon dots, somewhere we are giving some kind of microcapsules type of things. So, here these all are the plenty of examples by which we can use this kind of material in our day to day life. So, here before going to start, just let us know that how many sizes are available or maybe how many dimensions are available for using this kind of nanomaterials for our requirement. So, nanostructures are some 0, 1, 2 or 3 dimensional materials which are mostly composed of 1 dimensional and 0 dimensional nanomaterials such as nanopowders, nanoparticles, nanowires. So, when we are talking about any nanoparticles, the nomenclature of that nanoparticles is known as maybe the 1D, 0D, 2D, 3D like that. So, that D actually the by 2 method actually we can get the informations or maybe we can put the nomenclature of that particular nanoparticles. One is the confinement and unconfinement and another one is called the size, means x and axis, y axis and the z axis. So, nanostructures consisting of 2 dimensional nanomaterials arrangement or thin layers are called the nanocoatings or maybe the nanostructured coatings, because here maximum times we are using the film onto the substrate itself. That is why we are calling it as a 2D or maybe the 2 dimensional nanomaterials or maybe the 2D 2 dimensional nanomaterials coating. So, here this is also a beautiful example of Si3N4, that means silicon nitride. So, left hand side it is showing the scanning electron microscope image and the right hand side it is showing the transmission electron microscope image, where we can see that average particle size of that silicon nitride is 72 nanometer range. In the next also we are trying to discuss about the size dependency in nanostructure in terms of some kind of particle size and thickness of the nanocoatings. Already I have told you that term size dependency most of the times only concerned with the following 2 parameters. One is the particle size of the nanomaterials or maybe the grain size or maybe the crystallite size, and the second one is the thickness of nanocoatings or the nanostructures. That is how much layer, maybe a single layer, maybe a multiple layer I am trying to put onto my substrate or maybe that onto our materials. So, here these all are the different kind of characterization techniques by which we can prove that how much thickness we obtained after doing the coating onto the substrate itself, or maybe the what is the surface roughness or maybe the surface properties we are getting, or maybe that how the nanoparticles actually looks like onto the substrate itself. So, here first one is that cross section of scanning electron microscope image of the Ceria film obtained by sol gel methods. So, here we can see that this is our base materials, then the Ceria film has been formed onto the substrate itself, then in between that we are having some resins. So, resins is acting as a binder over there, so which is actually enhancing the adsorption properties in between the substrate and in between the coatings. So, by which that Ceria films is stick with the base materials. Here this one is called the AFM or maybe atomic force microscopy image. So, in which atomic force microscopy surface profile optimal nanocomposites coating, by which we can see that what is the surface roughness of that particular material, or maybe sometimes we can measure the particle size of that particular nanoparticles too. And the third one is called the bright field transmission electron microscope images of the nanostructure alumina. So here also we can see that what is the from just getting the dimension of this kind of nanoparticles or nanofillers, easily we can calculate what is the average size of alumina has been present in the matrix itself. Next, we are trying to discuss about the quantum size effect. So, quantum size effect in respect of the size dependency of that particular nanoparticles. So, quantum size effect, because of recent trend of downsizing, played a vital role in microelectronics and optoelectronic applications. It is normally used for the nanoparticles below 50 nanometer in size. So, when we are talking about the nanomaterials or maybe the nanoparticles, generally the scale is ranging from 1 to 100 nanometer, but when we are talking about the quantum size, that is well below than the nanometer range, that means it is below than the 50 nanometer range. So, it is normally used for nanoparticles below 50 nanometer in size. Coagulations and adhesions are the main problem in handling of such nanoparticles. Yes, of course, because when I am preparing my nanoparticles or maybe when I am making my nanoparticles more smaller and smaller, the surface area of that nanoparticles is increasing. Not only that, its aspect ratio is also increasing. So, due to that, there is a chance of agglomerations. All the nanoparticles is trying to stick together. So, that is known as the agglomerations, and or maybe sometimes it is known as the coagulations and also the adhesions, because they are so thin they can stick with each other, and then it is very difficult to make them separate. So, these all are the problems when we are dealing this kind of nanoparticles into the very small diameter. So, here also we are trying to give one classical example that quantum dots exhibit properties that are intermediate between those of bulk semiconductors and those of discrete molecules. Their optoelectronic properties change as a function of both size and shape. It is clear from the figure as the size of a particle decrease. So, you can see from this particular graph that size of that particular quantum dot is decreasing. So, when the size is decreasing, automatically the band gap is increasing. So, that is a very good promising materials for the semiconductor industry. So, then what again it is giving, that it is clear from the figure as the size of particle decrease till we reach a nanoscale, this makes the energy levels discrete, and this increases or widens up the band gap, and ultimately the band gap energy also increases. So, nowadays what we are trying to do, we are trying to use this kind of quantum dots materials. This is also a wonderful materials from the carbon groups. So, that materials actually we are trying to make it into the small size. So, we are trying to make those materials into the smaller size so that it can give the maximum band gap, so that we can get the maximum semiconducting properties from that particular filler itself. Next, that is also an example. So, here the example is that quantum size effect of titanium dioxide, silicon dioxide nanohybrid particles was discussed by measuring the band gap energy shift for titanium nanoparticles on the monodisperse silicon dioxide nanospheres. So, here actually the material is the hybrid composites. Initially we have taken the silicon dioxide spheres, on top of that we have done the modification by titanium dioxide. So, we have made certain kind of hybrid composites kind of thing, which we are going to use for some kind of electronic purposes or maybe some kind of other optical purposes. So, here from this particular figure you can see that we have given some kind of IR spectra or maybe that Fourier transform infrared spectra. So, in which we can see in the topmost phase, that is called the TiA2. In the anatase phase, you know that TiA2 can stay into the 3 different form. So, anatase is one of the most stable form where we can get or maybe we can put the TiA2 for a longer time, so that it will not decrease its properties. So, when we are talking about the TiA2, and then next sample it is showing the TiA2 SiO2 hybrid composites, and from that particular FTIR graph you can see that some graph has been shifted to the left hand side, which is showing actually the better entanglement in between the coating materials and in between the substrate materials, so that it is showing some kind of better properties. How it is showing the better properties? When we are talking about the particle size distribution, for TiO2 SiO2 hybrid sol gel and silica core particles, and the theoretical value in the dotted line, we are showing that when we are changing the particle size diameter into the nano level, so automatically some properties is getting increased for that particular case. The same thing has been proved by the some kind of FESM image and TEM image also. Here the TEM image, it is showing that core shell structure of that materials, in which we can show in the middle is the SiO2 silicon dioxide spheres can be easily seen, and the outside is surrounded by the TiO2 materials. So from that particular figure we can easily show that how the size dependency is affecting onto the semiconductor or maybe the some optoelectronics properties. Then we are trying to discuss that size effect on the thermal conductivity. Actually this topic is totally depends upon the size. When we are reducing the size of that particular nanoparticles, we are going to see that how the properties is changing, or maybe rather we can say that how the property of that particular composite is increasing, or maybe it is showing some other extra properties than before. So here in general, when the characteristic size like diameter of the particle will decreases, the thermal conductivity of the particles will also decreases. So here generalized result of the thermal conductivity of metallic nanoparticles to their characteristic size is illustrated in figure along with the copper nanoparticles. Polycrystalline silicon film shows strong reduction of thermal conductivity with respect to the bulk. So you see, when we are using this kind of materials and we are using the size of that particular materials or maybe the shape of that particular materials, automatically it is showing the better properties than the before. Not only that, low thermal conductivity in the case of microelectronic components leads to an increase in the operation temperature and earlier circuit failure. So when we are reducing the size, automatically we are getting the low thermal conductivity in future, which is helping us to increase the operation temperature, not only that the earlier circuit failure, so that the heat energy whatever it is generating at that particular point, slowly very quickly it is dissipating, so that that particular equipment or maybe the circuit or maybe the diode or maybe whatever the electronic part we are going to use, they are not capturing that heat. That means they are not heated up to certain temperature. So that heat is quickly dissipating. That means they are cooling down very quick, so that material machine fault or maybe that circuit fault may be stopped or maybe may be rejected. So here this is also the thing in where we can see that when we are going to increase the dimensions of that particular nanoparticles, so automatically the thermal conductivity is getting increased. So that means when we are going to the smaller size, then automatically the thermal conductivity of that particular material is getting reduced. Next is called the effect of size on corrosion phenomena. The same thing we can prove for the corrosion properties or maybe that corrosion resistant materials. So when we are using some kind of nanoparticles, if in the micro size whatever the corrosion properties it is showing, if we are trying to reduce its particle size, the corrosion property will be much better, or maybe that corrosion resistant property will be much better. The same thing has been shown over here also. So in that some literature it was reported that crystal grain size plays an important role in the resistance of passive films. That means corrosion behavior of nanostructured alloys has been mostly assessed by the electrochemical measurement. As the particle size approaches the nanoscale, the number of atoms in the grain boundaries increases, leading to dramatic effect on the corrosion phenomena. So this is the basic principle of this particular slide. The corrosion resistance of iron in alkaline solution considerably increased as the grain size decreased from microcrystalline to the nanocrystalline. So this is a very good example that where the size is actually creating some betterment in terms of the corrosion protections. So below is a figure where we are giving that potentiodynamic polarization curves of nanocrystalline iron with different particle size. So, you can see that we have given the graph in terms of 40 nanometer particle size, 20 micrometer particle size, 300 micrometer particle size. So, when we are talking about that smaller particle size, you can see the area is much broader. That means the corrosion resistant property of that particular material is tremendously increasing. Then the same thing we are trying to see in that particular case also, that is nothing but the effect of size on the gas sensitivity. Nowadays you can remember that we are using so many sensors, we are trying to make our all systems in our environment, in our car, in our industry, that fully automated. So, in that particular case we are trying to introduce the sensor each and everywhere. So, when we are making some kind of sensor, generally we are talking about the sensitivity of that particular sensor, then what is the hysteresis of that particular sensor, then what is the reproducibility of that particular sensor, or maybe what is the longevity of that particular sensor, and not only that, how fast that sensor can react, or maybe that how fast the sensor can work or maybe accept the results. That is also the main criteria for this particular gas sensor. So, when we are trying to use this kind of nanoparticles and maybe the small size nanoparticles, then we can see that the gas sensing properties of those materials is increasing tremendously. So, gas sensitivity depends upon two factors, namely the thickness of the grain boundary, that is known as the 2L, and the crystallite size, which is known as the capital D. So, in this particular figure I am trying to explain that how this different size is actually affecting the gas sensing technology. So, here when D is larger than 2L, here grain boundary contacts display higher resistance and govern the electric gas sensitivity of the chain, known as grain boundary control. So, here it is showing the low resistance at that particular point. When D becomes smaller and comparable to 2L, necks become most resistant and therefore they start controlling the gas sensitivity, therefore it is known as neck control. So, here you can see that particle size we are reducing. So, the same material is showing the better result than the previous one. So, in that particular case we are observing the high resistance. Finally, when D is smaller than 2L, the resistance of grain dominates the whole resistance of the chain, and the gas sensitivity in this case is controlled by grains themselves, known as grain control, and yields the largest gas sensor response in this particular case. So, the thing is that slowly we are trying to decrease the shape and size of that particular nanoparticles, so that we can get the better results in terms of gas sensing properties. Then there are several methods for producing the multilayers. So, actually till now we are discussing about the some kind of coating materials which we are using only a single layer or maybe the mono layer onto the substrate itself. But when we are talking about the multilayers, evaporation methods, high quality structures on atomic scale, electrochemical method, low cost for mass production, suitable magnetic properties, PVD and CVD plasma methods, preferably good mechanical and chemical properties. So, when you are talking about the multilayer, from the name itself you can understand that I am having the substrate, on top of that we are putting one layer of one materials, then on top of that layer again we are putting a layer of another materials. So, like that one by one, just we are making a sandwich like structure. So, a multilayer coating with different constituents is generally looking like this. It is an example where I am having the metallic substrate, on top of that I have put the oxide layer, on top of that I have put some kind of sol gel coating, then I have put some kind of sol gel with inhibitors and self healing agents which can act as a corrosion inhibitors migrations, then on top of that I have put some kind of sol gel top coat, and top of that we are putting some kind of weathering or maybe the loading damage. So, here the main function of this kind of coatings is that it can show several properties or maybe the several better properties than the previous one. So, from this particular material, that topmost cover it will not deflect or maybe it will not change into some sunlight or maybe into the rainy season, then it is having some kind of self healing agents. So if something, some cracks or pores can be taken place onto that particular coating, so automatically they can react together and they can make the chain once again. And also it is having the corrosion inhibitors, that means it can stop that corrosions, so that our substrate material not directly come into the contact with the environment, so that its corrosion properties will be diminishing. Next also we are trying to discuss about this type of hybrid nanofillers in terms of some properties. So first one is called the coating of TiO2 layer on the silicon dioxide monodispersed particles. So in this particular case what we are trying to do, the coating layer thickness of the obtained TiO2 silicon dioxide hybrid particles were estimated by 10 observations. So here in this case we are same thing, we are trying to make the silicon dioxide microspheres, on top of that we are doing the coating of the titanium dioxide materials. So the titanium and silicon ratio was changed from 0.1 to 1.0 in order to control the coating layer thickness and the crystallite size. By two method we can do this kind of things. Suppose in that particular case what is happening, we are having that silicon dioxide, titanium dioxide layer. So inside is our silicon dioxide materials, and the top of that we are giving the layer of titanium dioxide. So in this particular case we can do the two things, either we can increase the size of this particular silicon dioxide, so that automatically the titanium dioxide thickness will be reduced, that is one way, or maybe I can increase the size of the SiO2 and simultaneously I can increase the size of the TiO2. So there are two types of ratios can be obtained from that particular case. The same thing has been written over here, that 0.1 to 1.0 in order to control the coating layer thickness. So one case I am trying to increase the coating layer thickness, another case I am trying to increase the crystallite size. So both the cases I can check that whether our material is giving the better properties or not than the previous one. So in this particular case we are having a very good high resolution transmission electron microscopy image of the surface area of the obtained hybrid particles with Ti/Si is equal to 0.1 ratio. So where the titanium and silicon ratio is almost 0.1, and next we are trying to change the ratio thickness, and then in terms of coating thickness just we are trying to change its form into different value, and we can see that how the coating properties is changing. One case we have changed the coating size or maybe that coating thickness, another case we have changed the crystallite size, and after that we have seen that how much property or maybe the what better properties we are going to get. So here we are trying to discuss about some key features of the multi-layer coatings. So when we are talking about the multi-layer coating, which includes different piled materials on atomic scale, these multi-layer coatings are called the super lattice. In my last slide we have maybe last to last slide I have already told you that when on the substrate itself, when you are changing the different coating by layer techniques, we are calling it as a multi-layer coating. So here that multi-layer coating also sometimes known as the super lattice. These coatings having higher resistance against oxidations, higher hardness and longer life than those of single layer coatings, and strong coatings can be made using two alternative layers with high and low elastic constants. So here by these methods, maybe whatever the coating I am primarily doing, that we can protect that coating, or maybe we can enhance the properties of that coating, or maybe we can add some more harder material than the previous one. So by doing this one we can get the better properties by doing this kind of multi-layer coating. Each layer thickness must be in nano range, and there must be no dislocation source between layers. Also they must prohibit the creep along the layers. That means when I am using a one layer onto that substrate itself, that layer should be stick together, that layer should be homogeneously dispersed onto the substrate, then I am going to put the second layer, and second layer also will stick with that first layer in a very nice manner, it's not like that maybe some places the first layer is totally absent and the second layer is reaching and it is attaching with the substrate. It should not be like that. And not only that, during multilayer coatings, designing of both structural and constitutional factors must be considered. These factors are grain size, layers individual thickness, combination module, and the number of materials interfaces. So, these all are the key important parameters when we are trying to do the multilayer coating onto our substrate. Here is also one very nice examples has been shown that we are having some kind of carbide substrate, on that we are having some cobalt enriched layer which is giving you the toughness and fracture resistance. Then on top of that we are putting the titanium cyanide materials which is giving you the better adhesions, abrasives or maybe the mechanical wear resistance. On top of interlayer we are putting some kind of alumina structure which is actually giving some kind of adhesions in between the coating materials, because sometimes in between the coating materials also we need to put certain kind of binder materials or maybe the adhesive materials, so that both the coating layer can stick together and they cannot come out very easily, or maybe that layer separation should not be taken place. Then on top of that we are putting some kind of alumina which is giving you the chemical or maybe the thermal wear resistance, and top of that the last layer is known as the titanium nitride which is nothing but the wear indicator. So, by applying different materials layer by layer we can get so many properties from a particular materials or maybe from a particular sample. Next, what are the improvements generally in physical and mechanical properties through multi-layer and multi-constituent coatings? First one is called the physical and mechanical properties of some hard materials can be combined in multi-layer coatings, leading to optimization of material properties. Yes, of course, that actually totally depend upon our requirement. I can put some kind of soft materials, on top of that I can put some kind of hard materials, again top of that I can put some kind of soft materials. It totally depends upon our requirement. Abrasion is one of the most important factors for destruction of cutting tools, as they are subjected to high loads, high temperature and the inefficient lubrications. To improve cutting tools life, it is recommended to use some multi-constituents coatings such as titanium nitride, aluminum titanium nitride, aluminum chromium nickel nitride, because these all are the hardest materials. By simple way, if we want to make the cutting tool by this kind of materials, it will be very expensive. Not only that, maybe after certain time they can break, then replacing cost of that particular cutting tool is also too high. So, what we are doing, we are trying to use some kind of simple cutting tool made by the high speed steel, then we are doing the coating of this kind of materials on the high speed steel or maybe that HSS steel, so that material or maybe the some harder material can be cut easily, and then when the coating material will be worn out, then second times also we can coat the material. So, in a broader manner we can see that the cutting tool cost will be reduced, not only that the production rate will be very high. So, according performed studies, multi-layer coating of aluminum, titanium nitride, chromium nitride have highest abrasive resistance and hardness in comparison to other coatings. Multi-layer film of titanium nitride, aluminum nitride on metallic substrate also enjoys both high mechanical and oxidation properties. Not only that, it is giving you the some hardness or maybe the toughness to the cutting tool, sometimes it is giving you some kind of high mechanical and oxidation, anti-oxidation properties too. Then we are trying to discuss what are the advantage of multi-layer films over the single layer and what are the disadvantages. So, when you are talking about the advantages, a multi-layer film may have a better hardness and ductility as compared to single layer. A multi-layer film with limited thickness has equal or higher mechanical capability stability with each of single layers. There is an increase in cohesion between the multi-layer film and matrix. Remained stress in multi-layer film decreases. Multi-layer films have a more compact structure. So, these all are the added advantage. That is why we are going to use that multi-layer coatings on to some substrate just to enhance the so many properties at a time. Then of course there is certain kind of disadvantage, otherwise totally the research or maybe the development will be stopped. So what are the disadvantage? The basic disadvantage of multi-layer films over single layer is that it cannot transfer material properties to the surface. So it is not possible to use materials with their basic characteristics. That is the biggest disadvantage of this kind of multi-layer coating. Then multi-layer films may act as a light barrier in producing semiconductor wafers or and metallic dielectrics. So sometimes it can create certain problem for the electronic purposes. So that is also one kind of disadvantage for using the multi-layer coating on single layer coating. Then we have to come to the summary. So when we are summarizing this whole lecture, first we have discussed about the size, which is the size of particles or grain size, and thickness of nanostructure is a very crucial factor for nano applications. So as I told already, the crystallite size and the thickness of that coating are the two most vital parameters for this kind of coating techniques. Then nanostructures consisting of 2D nanomaterials arrangement or thin layers are most popular nano coatings or nanostructured coatings. Properties like mechanical, chemical, thermal, electrical, optical and magnetic are very highly dependent on particle size. Quantum size effect is mainly expected for the nanoparticles below 50 nanometer in range. It is more below than the nanometer scale. Sometimes multi-layered coating of nanomaterials are preferred over single layer coatings. For nanoporous materials, the nano size effect is determined by the number and the size of the pores. So these all are the main key factor of this particular lecture. Thank you.